Hey guys, welcome back to the Transformer Slam series. In the last episode, we started exploring vision transformers and we saw how the input tensors are prepared for vision transformers. We kind of covered this whole part where we talked about patchifying of the images, and then we talked about how it passes through linear encoding for feature size reduction if necessary, and then we also talked about positional embedding, how positional embeddings are added to the input tensor, and also how the class token is added. Now we are almost at this point, so now we will be entering into the transformer encoder part, and we will see how the transformer encoder works for the vision transformer. Uh, so the transformer encoder that you see here, this transformer encoder block, if we expand it, it looks something like this. So everything within the white dotted block is the transformer encoder, what you see here. Okay, so we'll be getting into this, and before moving ahead, actually I would like to talk about the Medium article that I shared last time. So I was talking about this Medium article by Rishabh Singh, that it gives a good insight into vision transformers. But I have found this article by Brian Pulfer to be better and more uh, practical in its approach. Also, at the same time, it gives a very good theoretical background. So we'll be following this particular article for our understanding. So let's just go ahead with this one. Okay. Um, now, now we will be talking about the layer norm or the layer normalization part. Now, what this does is it normalizes our input tensor. So if you remember, suppose this is our input tensor, and we have we have our values here, in all this places across this matrix. So what layer normalization does is that for each of the value, it normalizes it such that it is centered around 0 and the standard deviation is 1. So that's what this layer normalization layer does. Okay. And if you see here in this article, it's mentioned exactly what mathematical operation happens in the layer norm. um, it says that it subtracts its mean and divides by the standard deviation. Okay, so also one more point to note here is what I said earlier. It does such that it has mean 0 and standard deviation 1, but at the same time the shape of the tensor also does not change. Okay, so if you have a n you have a n cross 50 cross 8 tensor here, so the shape does not change after it goes through the layer norm, this one. um, Now we'll be seeing about the multi-headed self-attention and how that works. But before we get into that, we will just go over this whole transformer encoder block in brief to understand what's happening here. So here layer normalization happens to make all the value range between 0 to 1, right? To normalize basically all the value. Then we have our MSA block, we'll see in detail here. And then whatever comes as output of the MSA block, a residual connection goes from here and the value is added to get our final output. So this residual connection is added. You might have heard about the residual connections and the concept of it in something similar to RNN or residual neural network. Basically, what it does is that it retains the states of the past of the data so that at this point it's still able to relate it well to the past of the data, and the features in the past are still, like it's not lost, it's still valid at this point. Okay, so a residual block, a residual connection is added here, and then it goes through a layer normalization again. Again, the same thing happens, normalizing the data between 0 to 1. Okay, and then it is passed through a multi-layer perceptron. If you remember, MLP is nothing but multiple layers of fully connected networks. So suppose these are three layers, and all of them are interconnected. So that is what actually a multi-layer perceptron is. Basically, the whole thing is fully connected. This acts as a final learning block for the whole learning that has happened in the attention block, right? So attention block, basically what it does is that uh, it tries to learn the relationship between one part of the data to the other. Okay, and after that, whatever the learning has happened, this MLP block kind of is a final learning layer on top of it, and this also acts as a memory block to remember these relationships, and then it gives the output, and there is another residual connection that goes and gets added to the final output before the final output is given out as denoted as ZL here. Okay, so that's the overall thing that's happening here, quite straightforward, but this thing is what matters the most, so we'll be seeing that in detail. Now, once again, I would like to remind you all that this is our complete visual transformer architecture, and this part that we were talking about, the transformer encoder block, is this part, and this MSA part, multi-headed self-attention part, is this actually, which we'll be seeing in detail right now. Okay, so moving ahead, um, let me let me try to copy this. Okay, um, so at this point here, what we are seeing is that something, we can see something parallelly happening, something like that. But what actually happens here is, at this point we have our tensor, suppose like this, and we discussed that in our example we are taking it as 50 cross 8. Okay, so we have this tensor here. So what really is happening between this point and this point is, our tensor is divided such that when it is concatenated back again, right, the total size again becomes 50 cross 8. Okay, and the number of division that happens, I'm sorry, the number of division that happens will be the number of heads here, you know number of heads of this multi-headed self-attention block. So in this case, what you see here, 3, this 1, 2 and 3, is actually three heads of self attention. Okay. Okay, now going back to this stage, we will see what actually happens. So we have our tensor here, right? 50 cross 8. And then depending on how many number of heads we want, by the way, the number of heads should always equal to uh, the the feature size in each of the head. So in this case it becomes one single block, or sorry, one single block becomes size of 50 cross 4. Okay, so this 4 into the number of heads should equal to our total feature size, which is 8. Okay, so we will we will divide our tensor, and then each of these, okay, each of these, this one, this two, in this case we have like two heads, so each of this is passed through a linear layer on its own to give our mapping of query, key and value. Okay, so if you see um, in this article, see these three lines is what is actually creating the mappings. Okay, so if you see here, for n in range number of heads, okay, that basically means that, if our number of heads are 1 and I mean if our number of heads are 1 and 2, so for 2, for range 2, for each of those it will make uh, uh, it will make our data pass through this linear layer to have the learning. So going back to this, what this actually looks like mathematically is q, suppose we are doing it for query, wq into x. So suppose x is our data. In this case, this becomes our x, since it is already divided uh, into 1 and 2. Okay, so first time, for the first iteration of this loop here, this data goes as x. For the second iteration, this data goes as x. Okay, so what this gives us is, this will give us a query vector. Okay, a query in this case, sorry, it will be a query matrix of size 50 cross 4. Okay, this q will be the output here, but this wq will be learnt. Okay, this wq will be learnt. Why? Because if you go back and see here, it is passing through a linear layer, okay, which is like any regular fully connected layer. And what this means is that, it is parameterized such that whatever this represents, that will be learned factor. So that means that for first iteration, when this data goes in, we will have a learning of wq1. Okay, and for the second iteration, when this data goes in, we will have a learning of WQ2. So basically we will have uh, two two matrix, each of size 50 cross 4, containing the parameters that are containing learned parameters. Okay, and this q that you get here, also we will have like q1 and q2. Now we will see what happens with this q1 and q2, but one thing we need to understand here is that here also the same thing happens, and what we get is we get k1, k2, and v1, v2. Okay, and we also have our learned parameters wq1, weights wq2, wk1, wk2, wv1, wv2. Okay, now what happens is, if you know about attention mechanism, you would know that, the attention mechanism, the mathematical process that happens in attention mechanism is something like this. You have your q, you have your k, this is for transpose. Okay, so a dot product. Okay, and then it is divided by root of the dimension. So in our case, the dimension size is total dimension of this, which is 8. Okay, and this whole is softmaxed. So let me just move this here. This whole thing is softmaxed, and then it's multiplied by v, dot product. You can see the same process, this same process happening here, right? You have your QKV, which is your mappings, Q, K, and V mapping, and then Q is multiplied dot product by dot product of, the dot product is found between Q and the transpose of K, then which is divided by the root of dimension, which is softmaxed, and then this whole total thing again goes into the dot product with V. Okay, so this is exactly same as what has been discussed here. Now what this gives us is our attention. Now you may ask, how exactly does this give us our attention? So it's because, to give a rough idea, just to give a rough idea, what happens is you have your Q, you have your K. Okay, if you find a dot product between these two, you will get something like this, maybe M, where for each value you will have the relationship between each values, right? So basically it means that each point in the data will have the relations from each other. Now if I explain it in one dimension, it becomes more clearer. Let me try to explain it in one dimension. Suppose you had a vector q like this, and suppose you had a vector k. Doing a dot product of these two would give you a matrix like this. And for each of this would mean the relationship between this and this. This would mean a relationship between this and this. This would mean relationship between this and so on. Okay. Similarly, this would mean relationship between this and this, right? Here means relationship between this and this. Now, here means relationship between this, and so on for all the value. So, in this you can see how each of the point has a relationship, comes from a relationship between each of these points, right? Each of the point in Q and K, right? Same thing if you do it in two dimension with matrices, same thing happens, just that it's in higher dimension. Okay. And then again multiplied softmax. Why softmax is, why this matters is, why the soft maxing matters is, suppose here you got some value, here you got maybe a bigger value, here you got a bigger value, here a smaller, maybe here even smaller, here even bigger, here even bigger. Okay, so depending on how large the values are, that will show how strongly these values are related. Okay, so for this one, so suppose this is a very large value, that will mean that this and this are very strongly related, right? And if you softmax this value becomes between 0 to 1. And what that basically means is that the smaller the value, the more insignificant it will be, and the larger the value, the more significant it will be. Okay, so basically it highlights in this which is more significant and which is less significant, and that's how the attention works, right? The one that is more significant, there the attention is higher. Okay, so that's how the attention mechanism works here for query, key and value. Okay, linear blocks, I hope you understood. So basically this linear mapping that is happening for each of the part of the tensor, right? And then for each of those values we have our scale dot product attention, which is this what we discussed, this part or this part, right? This is the scale dot product attention that we discussed, right? Now after this this happens for each of the smaller block, each of these smaller blocks, and finally to get our 50 cross 8 block back, we concatenate all of this together. Okay, so that's what the concatenate here is. It's concatenating the results from each of the blocks. Okay, so 50 cross 4 we had, and if you concatenate it back for two heads, we will get it back as 50 cross 8. Okay, and then linear mapping again, and then the final output is what we get here after the linear mapping. Okay, so after this linear mapping, the final output is what we get here, to which, as we discussed, a residual connection is added. Okay, so I think in this we covered each part. So We covered the how the transformer encoder is working. Previously, we discussed about this input tensor and positional embedding class tokens. Now we discussed about how the transformer encoder is working. And within the transformer encoder, we focused on the multi-headed self-attention, and we saw in detail how the multi-headed self-attention is working, right? So now we are able to understand this whole thing. Again, as I mentioned, there's an MLP classifier here, but works as just any other MLP classifier to have just that final level of learning and a memory kind of thing. So now we know how the whole uh, how the whole architecture of vision transformer works. Now after this, at this point, what you will basically get is a 50 cross uh, sorry, let me 50 cross 8 size of tensor, where the first one will be the class token that has gone through all the processes that we discussed here. All these processes. This class token has also gone through all the processes because it was part of it. Now, for finding this class label, finally what we do is we extract this class token and then we pass it through a softmax function to finally have our class label. Okay, if you see here, you see after the MLP, it's again finally softmaxed, and what we get out is the logits which belongs to each of the classes. So that's how the vision transformer works. I hope I was able to explain it clearly to you guys. Now in the next episode, we will be implementing a small vision transformer. Now since we have seen the vision transformer in complete detail, we don't really need to follow this complete big chunk of code, because understanding was mainly important. Now at this point, what we can do is we can go ahead and we can have a pre-trained vision transformer model from Hugging Face, and you can use that for our purposes. Okay, so next what we will do is we will use a simple vision transformer to do classification task, and then we will visualize the attention maps in that. Okay, so I hope this was helpful, and I hope you all are learning along with me, and I hope I'm able to do a good task of you know sharing my learning, so that in a way that it's helpful for you guys as well. So there's still much more to come, so stay tuned.